The session should give you an understanding of the components of Conformiq designer models and how you approach the task of modeling a system for test generation. The models for Conformiq designer are written in a language called QML. And there are three main components to a QML model. System block is the definition of our black box. It defines the interfaces of the black box as well as the interactions on these different interfaces. Then you can use UML diagrams to define the class structure of the model, as well as state machines with which you can use to define the stateful parts of the behavior of your system. Then we have a Java-like action language which you use, for example, to define the conditions for the transitions, as well as then the actions that take place when a certain transition is executed. Models can also be created fully just using the textual Java notation, but most typical models for Conformiq designer also have the state machine part created using the UML state machine diagrams. So the system block is the definition of our black box. The tested system in real life is always accessed through a set of interfaces, an API, user interface, protocol message interface, etc. And the system block is a mapping of these real interfaces of the system using the concepts of the modeling language. And it then defines the language for the tested system, how the tested system and therefore also the model interacts with its environment. So the system block defines the individual interfaces of the system. Here we see two interfaces, one on the top and one here on the left. And then it also defines all the possible interactions on these interfaces. You could have one incoming interaction on this interface, two outgoing, and then maybe three incoming here and two outgoing interactions here. Then the state machine parts define, you typically use to define those parts of the functionality of the system which lend themselves naturally to a stateful description. And as the name suggests, the main component of a state machine is a state. Here we see one state called name. And the way you should think of state machines is that at any given point in time, the execution of a state machine is in some state. Then at the occurrence of a certain timeout, or upon receiving a signal from the environment, the execution or the state of the state machine changes through a transition. So the transitions are these arrows here connecting different states to each other, and then to the transitions we have connected this action language which defines first of all the conditions for triggering the transition, and then after the slash here the actions that take place when this particular transition is executed. Here we see an example of a signal trigger, which means the way you read this is that this particular transition is executed when in this state on port B, which is one of the incoming interfaces of our model, we receive a message called type, and if then also when the message is received, this guard, which typically can check certain whether certain conditions in the incoming message hold. If the guard is true, then the action following the slash here is executed, and a state change occurs, which in this case means that the execution goes from the name state here to the final state of the state machine. And then that's how you then create state machine. You look at the different states of the system, you connect them with the transitions, and then you put the conditions for the transitions between the states on the transition arrows. Then if we look at some of the other components that we have here, we had here the state, the final state, which is the endpoint for the execution. Here we have the initial state where the execution of a state machine starts. So we go here, then start waiting for this message on port B, or this timeout to occur, or this message on port A to arrive. This transition here is a special internal transition, which means that when this transition is executed, there is no state change in this state machine. So the execution remains in this very same state. It just executes the actions in the transition. Then we have here two other interesting elements. There is something called entry and exit, and what these mean is that they are the entry and exit actions of the state. Entry action is always executed whenever you come to this state from outside. So when we come from initial state through this transition to this state, then these actions here in the entry part are executed. And then obviously for exit actions, the rule is that whenever we leave this state, either through this transition, when this timeout occurs, or through this transition, when we receive this message through port B, then the exit actions are executed. Then what we have here also is a symbol for a substate machine. Substate machines are an important concept in UML state machines, because they allow dividing the state machines into levels of hierarchy, which means that when you create a state machine, you don't have to put all the states of the state machine on one flat plane, but you can hide details that pertaining to, for example, this name state here in a hidden hierarchy or substate machine, instead of just putting all the states here on the same hierarchy level. So this is the same kind of thing that where in Java programming you hide the details of certain detailed functionality into a function, and then you make a call to this function. In a similar fashion, in the state machine, you can create substate machine which hide the details of the stateful behavior of the system, thus making it easier for you to understand and also maintain the state machine. Basically here we have almost all the fundamentally important components of UML state machines. This is a simple example, but complex state machines, they use the same constructs. It's just a matter of knowing the rules of the execution for these UML state machines, and then connecting these different components to create the stateful behavior of the system. Then the actual language that is used in QML models is Java, and therefore the data types available in the language are in practice almost identical to Java. There are some extensions to the data type system, such as these ports, which are the interfaces that you define in the system block. And then we have records, which are then the messages or individual interactions that are defined on the ports of the system block. But other than that, the data type system in QML is very similar to Java. And if you're familiar with Java, or let's say C# for that matter, it should be very easy for you to understand how to use and how to manipulate data in QML models. And not so surprisingly, since the language is essentially Java, the control flow in QML models is done exactly the same way as it is in Java models. For branching, we have if statements, we can have conditional expressions. For iteration, there are while loops, for loops, and do while loops. And then we can have procedure calls, which can be recursive. So all the basic concepts of a programming language are available when you are creating models for QML. And then in the end, here is an example of how these different components are used to create a complete model. A very simple one, but still a complete model that you could have Conformiq Designer generate tests from. So let's look at what this model here consists of. First of all, we have the system block, which says that our system has one incoming interface where the system accepts messages called message. Then it has one outbound interface where it can send the same messages. So it gets a message, sends a message out. Here we have then defined this message which we are referring to here in the system block as a record. A simple record, no data, just a signal kind of a data type definition. Then what you typically always do in Conformiq Designer models or QML models is that you define a class as a state machine, which then represents the functionality of the system that you are modeling. So here we have a one-liner in the textual part of the model which says that we have a class called myEcho, which extends state machine. And then in the textual part what we have remaining in the textual part is this main entry point of the model. So exactly the same way as in Java, we have a main entry point for our model, which then starts the execution, which in this case creates an instance of our state machine and starts the execution of the state machine. The only difference to Java here is that in Java this of course would have to be a member of a class, but in QML the main is a global function. Then corresponding to this textual definition of our model, we have this thing that we have created then as a UML state chart, which defines the behavior of the model. It's called myEcho. It has the same name as this class definition here, which is the connection between the state diagram and the textual definition. It has an initial state, a transition, then the state, a concrete state, and then a name for the state. And then inside the state we have one internal transition. And what this specification now says is that our system, when it's started, it stays in this one echo state, receiving messages from this inbound port called in, and as soon as it has received the message, which is then defined by this action here on the second line, it sends or echoes the message back. That's where the name of this model comes from. It echoes whatever it receives, well, not whatever, but the message that it receives from its environment, it echoes immediately back. So it's an echo model. And if you now give this model to Conformiq Designer, you would get out one test case which would be enough to exercise this particular system, because the functionality is very simple. We receive something and then we send the same message back. And that's it. A simple example, but bigger, more complicated models, they follow, they are exactly the same. They have the system block, a class as a state machine, and then you have the states and transitions in a diagram, and then you can have details of your model defined inside the class in the textual part of the model. And that's it. As simple as that.